emulsify, and you should be left with a beautifully emulsified black garlic sauce. This emulsion will break easy, so keep it warm, but don't let it boil, don't let it simmer whatsoever. Just salt, and that's done. Now, the peaches will go brown if you pickle them in a jar. So simmer, making what I'm calling a fillet is ready to go. Look at that crust. Now, let's put it back together.
We're just gonna wait a few more minutes, I guess, guys, and see if anyone else joins or not. All right, well, it's 6, so let's go ahead and get started, guys. So, like always, I have my own review. I have a total of 12 problems to do. They're all going to be based off of the homework. And this is going to get started. So I'm starting with number 30 on the homework. So number 30, what I want to do is, or what we want to do is we want to reduce this down as much as we can. So I have the cube root of 3 minus 2 root 5 all raised to the 21st power. So the first thing I'm going to do with this problem is I'm going to see, well, what's going to be bigger, 3 or 2 root 5? Right, because it's 3 minus 2 root 5. So 3 is the same thing as a square root of 9. And 2 root 5, that's the same thing as, that's the same thing as the square root of 20. So in this right here, the square root of 20 is bigger than the square root of 9, which means 2 root 5 is bigger than 3. So what that tells me is that when I subtract 3 minus 2 root 5 to the 21st power, I actually don't even need to do that. I'm sorry, I don't need to do that because it's an odd power. You only need to do this when you have an even power to an odd. I'm sorry about that. Yeah, we don't need to do this actually, because we're going from, we have an odd power and we take the square root of it. We just end up getting 3 minus 2 root 5 to the 21 over 3, which is the same as 3 minus 2 root 5 to the 7. And that's actually what your answer is going to be. All the stuff on the right, don't worry about it. I kind of just got a little too excited and went about the wrong way. But basically, for number 30, I have the cube root of 3 minus 2 root 5 to the 21st power. I have an odd power going to another odd power, so I don't need to worry about any absolute value signs happening. So 3 minus 2 root 5 to the 7th power is going to be my answer. Any questions about that? Anand, go ahead.
Why didn't you simplify it?
Sorry, say it again.
Why didn't you simplify it?
What do you mean simplify it?
Like simplify 3 to the 3 to the root of 7, and then why didn't you like simplify it further?
You can't really simplify it any further than here. Do you mean like why am I not distributing the 7 to each
Yeah.
power? You
Yeah.
can't do that because there's a negative sign right here. If we had something like 3 times 2 root 5 to the 7, then I can distribute out that 7 to 3 and 2 root 5. Because it's 3 minus 2 root 5 to the 7, you're multiplying 3 minus 2 root 5 to itself 7 different times. So you can't really reduce it any more than this.
Okay, got it.
Make sense? Some more people joining. All right, great. Okay, so let's go on to the next problem, which is number 32. So for number 32, I have the square root of 12 minus 5 root 6 to the 26th power. So for this one, obviously it's a square root. So when it's a square root, that means we have an even power and have an even root, and an even power. So I can rewrite this as 12 minus 5 root 6 to the 26 over 2, or 12 minus 5 root 6 to the 13. So I went from an even power of 26 to an odd power of 13. So that means I need to put absolute value signs around this, but I only really need to do this if 12 is smaller than 5 root 6. Because remember, these are real numbers, so I know exactly if it's going to be positive or negative. The reason we put absolute value signs around variables like x's or y's or z's is because we don't know if they're positive or negative. But in this case, I can figure out if 12 minus 5 root 6 is positive or negative by kind of comparing them and seeing which one's bigger. So 12, that's the same thing as the square root of 144. 5 root 6, well, that's the same thing as the square root of 25 times 6, which is 150. So the square root of 150 is bigger than the square root of 144. So that tells me that 5 root 6 is bigger than 12. So that tells me that 12 minus 5 root 6 is going to be a negative number since 12 is smaller than 5 root 6. So that means if I want to have an answer for this problem, I need to put absolute value signs around this answer. But because they're real numbers as well, I can actually kind of get rid of it. I can rewrite this. I can get rid of the absolute value sign, sorry. I can get rid of them because I know exactly what the value is, and I can kind of factor out a negative. This middle part, I can rewrite it as, go back to black. I can rewrite this as negative of negative 12 plus 5 root 6, absolute value of all this to the 13th power. And then we take the absolute value of this negative number, this negative right here, and the rest of this. What you end up getting is that the negative kind of goes away, and we're left with the absolute value of 5 root 6 minus 12 all to the 13th power. That's the same thing. All I did was flip the side. Instead of negative 12 plus 5 root 6, I'm writing 5 root 6 minus 12. But at this point, I know 5 root 6 is bigger than 12. So when you subtract those together, I'm going to get a positive number anyway. So that absolute value sign isn't necessary. And I can just write this as 5 root 6 minus 12 to the 13th power. And that's going to be your answer for that. Any questions about that? Are we okay? Arjun, go ahead.
Can you explain how the absolute values work again? Like for which powers?
If you go from even to odd, you put absolute value signs. Because if you have an even power, what's inside of it is always going to be positive. So when you go from an even to an odd one, that means, well, if what's inside of it's negative, in the original equation that you have, before you reduce it, you have a positive number. But when you reduce it to an odd power, if you have a negative inside of it, it could become negative. So you need to make sure
Okay.
it's consistent with the beginning, and you put absolute value signs around it.
And is it the same with like square roots, like the power for the square root?
I'm sorry, say it again.
So do you have to do the same thing if it's like the square roots, like thing, number? I don't know what it's the index.
Oh, like
Or
if I just have a square root, so like if I like
like
this,
if it's like a sixth root and it becomes like a third root at the end, do you also have to put like absolute values?
if you go over, yeah, if you go from an even power to an odd one, always, yeah, but go ahead and just put absolute value signs. You're gonna have to.
Okay.
Um,
So like even if it's like I meant like a square root, like the little like the number is like 2 and like a cube root it's like 3, right? So
yes,
like if you so you also have to do that for square roots, like put absolute values.
even roots, yeah. It's like
Okay.
2, 4, 6, whatever. Yeah.
Okay.
All right, Ajay, if you start from odd, you don't have to do all this stuff, all the absolute value stuff, right? Yeah. If you're starting from an odd power, like we did on number 30, yeah, don't make the mistake of even worrying about what's bigger, 3 or 2 or 5, because I start from an odd power of 21. I don't have to worry about it at all. I go, even if I went from 20, I went from 21 to 7, so I don't need to worry about it at all. So yeah, you don't worry about the absolute value stuff. You go over the parts in green, like why you factor out the negative, why do you factor out the negative? Okay, so a couple people are wondering why we factor out the negatives. Let's go ahead and do this again. So what's happening when we're factoring out the negative and why we're doing it is because what I want is I want to rewrite this equation in a way that 12, what's inside the what's it called? In the parentheses, is going to be positive. Because right now, 12 minus 5 root 6, that's a negative number, right? Because I saw on the right side, this part in blue, that 12 is smaller than 5 root 6. So 12 minus 5 root 6 is going to give you a negative number. So I don't want to write in that form. I can kind of play around with the equation. And I can basically say, well, if I rewrite what's inside of it to negative times negative 12 plus 5 root 6, the absolute value of all that to the, I'm not sure I was writing in red, but all that to the 13th power. This is the exact same thing. If I took this negative and I distribute this back in, I'm going to end up in the same exact equation I was above. So I didn't change the value of the equation. And you guys remember back from, I think, module 2, when we did absolute value signs, if I'm multiplying something with an absolute value, so like an absolute value of negative 12 plus 5 root 6, I can kind of apply that absolute value to every single thing being multiplied together. So I can rewrite this as the absolute value of negative 1 multiplied by the absolute value of this negative 12 plus 5 root 6. And then obviously all this to the 13th power. So you can rewrite the absolute value signs in that way because that negative that we pulled out is being multiplied with everything in the parentheses. So when you do that, you can apply the absolute value to every single thing being multiplied together. In this case, the -1 and what's inside the parentheses. The absolute value of -1 is just 1, so that kind of just goes away. And all I'm left with is the absolute value of this second part in blue right here. This part right here, I'm left with that, which is -12 plus 5√6, absolute value to the 13th power. So I'm at this part right here, and -12 plus 5√6, or I can rewrite this as 5√6 minus 12. That's going to be a positive number now, because 5√6 is bigger than 12. So when 5√6 is bigger than 12, when you subtract them, you're going to get a positive number. So those absolute value signs are kind of unnecessary. And you just have 5√6 minus 12 to the 13th power. Ibrahim and Anand, does that make sense? Perfect. Anand, how about you? Good? Thumbs up, great. Okay. So with all that said, I do want you guys to understand what's happening. But really what's the shortcut here is that if you go from an even to an odd and you have 12 minus 5√6, all we're really doing is flipping these two numbers and getting rid of the absolute value signs. Because you're allowed to do that. All you really end up getting from the beginning is just become 5√6 minus 12 because you flip those two numbers to the 13th power. But everything we did in red and green, whatever the colors were, it's good to know so you understand really what's happening rather than just kind of going through the motions kind of robotically, not understanding what you're doing. All right, with that said, anything else or any questions about this problem before we move on? Okay, let's keep going. Number 34. So for number 34, we have the 6th root of 64, v to the 12, w to the 60, x to the 90, y to the 108, and z to the 222. Okay, so what I'm going to do, or what we do for these types of problems is I'm going to prime factorize everything that I can. So the v to the 12, the w, x, y, z, that's all fine. But that 64, I'm going to rewrite it as this prime factorization, which is 2 to the 6. So I can rewrite this as the 6th root of 2 to the 6, v to the 12, w to the 60, x to the 90, y to the 108, z to the 222. All right. So I can rewrite it this way. And I'm going to start taking what I'm going to start looking for now is I'm going to start finding groups of 6 in these exponents. And that's how many groups I can take out. So for instance, I have 2 to the 6. Well, how many groups of 6 can I make out of 6 2s? I can make one group of 6. And I have 0 left over, so I don't have to put anything inside the absolute value. After that, I have the v to the 12. Well, I can take out 2 v's. I can take out 2 v's, and I have nothing left over, right? I can make 2 groups of 6 v's. So I have two groups. I take it out, and I have nothing left over. For w to the 60, I can take out 10 groups of those, and I have nothing left over. For the x, at x to the 90. For the x's, let's see what that is. I can take out 15 groups of x's, so I have x to the 15 with nothing left over. For the y's of 108, that's going to be 18. I can pull out 18 y's and have nothing left over. And then for 222, I can pull out 37 z's out of 222 z's. So let me go ahead and move this over a little bit. I can pull out 37 z's. So when I pulled everything out, this is what I get. I have nothing left over, nothing left in the roots. So I don't have to worry about that. What I do have to worry about is where do I put my absolute value signs? Because all these inside the root, these are all even numbers and have an even root. So I need to worry about, well, where do my absolute values go? And they only go if you go from an even to an odd number. So my 2's go from 6 to 2. I don't have to worry about that though, because 2 is already a positive number. Putting an absolute value of 2 doesn't really do anything. My v's go from 12 to 2. 2 is even, so that's fine. W's go from 60 to 10. 10 is even, that's fine. X's go from 90 to 15. Well, 15 is odd, so I'm gonna have to put an absolute value sign around that. My Y's go from 108 to 18. 18 is even, so that's fine. And my Z's go from an even of 222 to 37, which is odd. So we need to put absolute values around that as well. So all we're going to do now is just rewrite it a little nicer. So we have 2v squared. That's supposed to be a w to the 10 times the y to the 18 multiplied by x to the 15 z to the 37. So just pull everything out. Anything that went from an even power to an odd one, put an absolute value sign. In this case, it was only the x and the z. Any questions about that? Does that make sense? If not, let's keep on going. All right, number 36. So I have 3 to the 1/2 times 3 to the 4/3 and 3 to the 1/6. So I want to combine, I'm multiplying these all together, so I want to combine them. And since they all have the same base, what essentially is happening is that I get 3 to the 1/2 plus 4/3 plus 1/6. That's essentially what's happening. So I need to add 1/2, 4/3, and 1/6. Well, the common denominator there is going to be 6. So I have 3 to the 3/6 plus 8/6 plus 1/6, which will give me 3 to the 8, 9, 10, 11, 12, 3 to the 12/6, which is 3 squared, which is ultimately 9. So this is one of the rules we talked about since one day. You multiplying stuff with the same base, you can add the exponents, which is what we just did. We add them up, you get 3 squared, which is 9. Any questions there? Are we good? Okay. Number 37 of x to the 3/10 over y to the 7/6, all raised to the 15/7. So first thing I'm going to do is distribute this 15/7 to top and bottom. So when we do that, what we end up getting, 37, is x to the 3/10 multiplied by 15/7 all over y to the 7/6 multiplied by 15/7 as well. So when I do that, what I get is that these 7s cancel out, and the 6 and the 15 I can reduce to 2 and 5 because they're both divisible by 3. So on the bottom, what I'm left with is y to the 5/2. And on the top, I have 3 and 7. That doesn't really reduce, but 15 and 10 do. The 10 and the 15 are both divisible by 5. So I get 2 and 3. And what I'm left with is x to the 6/7. Or, sorry, 9/7. We'll multiply those. Am I forgetting how to multiply? Yeah, 9/14. All right, so that's what I end up getting, x to 9/14 all over y to the 5/2. But we're not done here yet, because the problem here is that I have y to the 5/2 in the bottom. And what that means, what that is that's the same thing as saying, well, that's y squared times the square root of y. They're equivalent, they're the same thing, right? I can make 2 groups of 2 out of 5 y's, so I have y squared times the square root of y. So x to 9/14, sorry. So I don't want that square root of y in the bottom. So I'm going to take that square root of y and multiply with top and bottom. So I have x to the 9/14 all over y squared times the square root of y. And I'm going to multiply top and bottom by the square root of y, because I don't want any roots at all in the bottom. You don't want any roots, and you don't want any fractions of exponents on the bottom as well. So what we end up getting is x to the 9/14 multiplied by the square root of y all over the square root of y times the square root of y just gives you y, so we have y cubed. And that should be your answer. Any questions about that? Rebecca, go ahead.
Why did you just get rid of the 5?
This 5 over here.
Yeah.
So I didn't get rid of it. So the y to the 5 over 2, that's the same thing as saying the square root of y to the 5, right? So
Yes.
I can pull out two groups and have y squared times the square root of y.
Then why does the 2 go away in y5?
The 2 in the bottom.
Yeah, like on the purple. Yeah. Oh, okay.
Remember, the square root is the same as the second root. So you have the square
Yes.
root or the second root of y to the 5th, which becomes y squared times the square root of y, which is what I have here. But then you get rid of that square root of y, which is what we did when we rationalize it.
Okay, thank you.
No problem. Any other questions about this problem? Are we okay? Ready to keep going? Great, let's keep going. 41, I have the cube root of 5 times the 6th root of 5, number 41. So for this one, I'm going to put them both as exponents. So I have 5 to the 1/3. I'll do 1/3. But 5 to the 1/3 times 5 to the 1/6. This is the same thing. I just put them in exponential form. And since I'm multiplying stuff with the same base, I can just add the exponents. So I have 5 to the 1/3 plus 1/6. 1/3 is the same thing as 2/6 plus 1/6. So you get 5 to the 3/6, which is the same as 1/2. So it's the square root of 5. Any questions about that? Does that make sense? All right, let's keep going then. Now our number 44. So number 44, I have the 4th root of 64, x to the 18th, y to the 36. So same thing as we said before. The first thing I'm going to do is prime factorize it. So the only thing I'm going to do that with is the 64. 64 is the same as 2 to the 5th, x to the 18, y to the 36. So it's the same thing. And I'm going to do the same thing I did before. See how many groups of 4 can I make with all these exponents. So I have 5 2s, so I can make a total of one group of 4 with 1 left over. I have 18 x's. Out of 18 x's, I can make a total of 2 to the 5th is 32. 2, 4, 8, 16, 30. It is. What do you know? I can't do math. Yes, 2 to the 6th then. Thank you. All right, so 2 to the 6th. So I pulled out one group of 2, and I have two 2s left over inside. Thank you for that. I have 18 x's. I can pull out 4 groups of those, and when I do, that's a total of 16 x's. So I have 2 x's left over inside, and then I have y to the 36, and when I pull those out, I can make a total of 9 groups of 4 out of those. So I have 2 x to the 4th, y to the 9. But again, I have an even root, right? I have even exponents here and even root. So if I go from even power to odd power, I have to put absolute value signs. The real numbers, I don't need to worry about them because, well, they're real numbers, right? I know exactly what their value is if they're positive or negative. With the variables, I don't know. The x's go from even to even, so x is fine. The y goes from even to odd. So that means that the y needs an absolute value sign. And that's multiplied by the 4th root of 2 squared x squared. But if I look at this 4th root of 2 squared x squared, these are all divisible by 2. Or in other words, if I was to take this part right here and rewrite it as an exponent, this is what I get. If we distribute this in, you get 2 to the 2/4, x to the 2/4, or simply just 2 to the 1/2, x to the 1/2, which gives you the square root of 2x. So this whole part right here, I can take all this and I can rewrite x to the 4th, y to the 9. I can rewrite that radical part as the square root of 2x. But again, because I'm reducing the power of this x from an even power with an even root, I have to be careful with how that power ends up at. So I start with a power of 2, and then I end with a power of 1. So that means this needs to get an absolute value sign. And this ends up becoming your final answer. So even if it stays inside the root, it could get an absolute value sign. Alden, go ahead.
So you put the absolute value sign around the x, but what about the 2? Like, wouldn't it be technically the 2 to the power of 1? So
It is.
isn't that also odd?
No, you're 100% right. So technically you're right. We should be putting an absolute value sign here, right?
Yeah,
What's the absolute value of 2 though?
just 2.
Just 2. So there's no point to put them. Like you're not wrong. They go from an even power to an odd one. You're right about that. So technically they do get absolute value signs, but the absolute value of 2 is just 2. So there's no point to put it. It's like the same reason on tests, we don't say, oh, this is x to the first power times y to the first power, whatever it is. Like you don't say y to the 1 equals m to the 1 x1, right? Y equals mx plus b to the first power. You never say that, right? This is kind of redundant. It's the same thing as saying absolute value of 2. It's just, there's no point to it because we know that the value of absolute value of 2 is just 2.
Okay, so the rules do apply, just we don't need to really write it on the real numbers because
You know their value.
yeah.
Yeah, it still does apply exactly. It just there's
Okay.
no points.
Okay, it's just we don't write it because it's
It's
easier.
redundant.
Okay.
Yeah, exactly.
Okay. Thanks.
No problem. Any other questions here? Are we okay? Ready to keep going? Okay, let's keep going. Number 47. So for number 47, I have the 4th root of 4, the 3rd root of 3, and the 6th root of 6. So the first thing I'm going to do in solving this out is I'm going to rewrite this all as exponents. So I have 4 to the 1/4 times 3 to the 1/3. It's an ugly 3, but actually we should rewrite it. All over 6 to the 1/6. So I have 3 real numbers and 3 different exponents, and everything's different, right? But there's still a way to combine these. And you can do that by making the base, or sorry, the denominator of each of these exponents, make the denominator of each of these exponents the same, and then you can factor that out, and you can kind of reduce it from there. So I have denominators and exponents of 4, 3, and 6, what I underlined in green. And the common denominator of all that's going to be 12. So I can rewrite this as 4 raised to the 3/12 multiplied by 3 raised to the 4/12 all over 6 raised to the 2/12. So I rewrote these so the exponents all have the same denominator, because when you do that, I can rewrite this again as 4 to the 3rd times 3 to the 4th all over 6 squared, all raised to the 1/12 power. So this is what I have now. I basically factored out a 1/12 out of the exponent, because I can see if I distribute this 1/12, I took this 1/12 and distributed it back into each of these, I end up at 4 to the 3/12, 3 to the 4/12, and 6 to the 2/12. It's the same exact thing. And then from here, what I can do is I can kind of reduce what's happening inside of it. I have 4 to the 3rd times 3 to the 4th times 6 squared. I can reduce what's happening inside of here, because I can rewrite this as, well, 4 is the same as 2 squared to the 3rd times 3 to the 4th, and 6 is the same thing as 3 times 2 all squared. What I'm basically doing is find the prime factorization of all these numbers. So when we reduce this again, 2 squared to the third power is 2 to the 6 times 3 to the fourth, all over 3 squared times 2 squared. Let me go ahead and mute you. I don't want to hear myself. Okay. So I have 2 to the 6 times 3 to the fourth, all over 3 squared times 2 squared. And then from here, I can start reducing these 3's and 2's. This 2 squared cancels out. All right, please keep yourself muted, or I'm just going to kick you out. All right. And that becomes 2 to the fourth. I can cancel out this 3 squared, and this becomes a 2. So what I end up getting is 2 to the fourth times 3 squared, all to the 12th power. And then just like before, or sorry, 1 over 12, sorry. And then I can distribute this 1 over 12 inside of it, or really a shortcut is to see that 4, 2, and 12 are all divisible by 2. So you can reduce all these by 2 and get 2, 1, and 6 to end up getting 2 squared times 3 to the first power all over 1 to the 6th, or the 6th root of 12. And that's going to be your final answer. Will I be posting the tutorial video? That's the goal. Yeah, it's recording right now, so hopefully it stays recording. I'm able to post it, so I should be posting, hopefully. But any questions about this problem right here? Are we okay with this? You do need to reduce it all the way down to the 6 root of 12. Any questions, comments, concerns, or are we ready to keep going? Okay, let's keep going. Number 48. For number 48, I have the second root of 10 times the fourth root of 20 times the eighth root of 50. So just like always, I'm going to be putting this in exponential form. This makes it a little easier to work with. So I have 10 to the 1/2 times 20 to the 1/4 times 50 to the 1/8. And then what I'm going to do here is I'm going to do what I did before. I'm going to find the prime factorization of 10, 20, and 50. So I have 5 times 2 to the 1/2 times 5 times 2 times 2 to the 1/4. That's 2 times 2. And then 5 times 5 times 2 to the 1/8. And what I can do from here is I can distribute in these exponents into each of these terms. So what I end up getting is 5 to the 1/2 times 2 to the 1/2 times 5 to the 1/4 times 2 to the 1/4 times 2 to the 1/4 times 5 to the 1/8 times 5 to the 1/8 times 2 to the 1/8. So I can distribute these exponents inside. All right, and when I do that, I can see that, well, I have a bunch of 5s being multiplied together, and also a bunch of 2s being multiplied together. So what I'm essentially going to do is just rewrite this, but add up the exponents for all the 5s and the 2s. So my 5, I have 5 to the 1/2 plus 1/4 plus 1/8, right? 1/4, 1/2, 1/4, 1/8, and another 1/8. And then for the 2s, I have 1/2 plus 1/4 plus 1/4 plus 1/8. So I can combine this really expanded out series of 5s and 2s raised to different exponents into this condensed form right here. And when you do, well, 1/2, for the 1/2, 1/4, 1/8, 1/8, they have a common denominator of 8. So I can rewrite this as 5 raised to the 4/8 plus 2/8 plus 1 plus 1/8. 1/8 plus 1/8, sorry, is another 2/8. And then for the 2s, I have same thing, common denominator of 8. So I have 4/8 plus 1/4 plus 1/4 is 2/4, which is the same as 4/8. So we can go ahead and write that as 4/8. plus another 1/8. So the 2's, you add them up, you get 9/8. And for the 5's, we end up getting what, 4, 5, 6, 7, 8. 8/8. So 5 to the 8/8 is just 5. But for the 2's, I have 2 to the 9/8. So that's the same thing as the 8th root of 2 to the 9 power. I can take out 1, 2. And when you do, you multiply with the 5 to get 10 to the 8th power of 2. So a lot of this stuff is really just playing around with what you have, seeing what you have, and breaking it down to see what you can do. But any questions about this problem right here? Are we okay? Comments, questions, anything? Okay, let's keep going. Number 69. So I have root 2 minus the cube root of 2 all squared. So to solve this problem, we're just going to multiply it out and see what I can do from there. So I have root 2 minus the cube root of 2 all squared, which means you multiply them together. Sorry, it should be a minus, not a multiplication. So let me multiply these together. So you could put this into exponents if you want to. That's perfectly okay. And that's actually how I prefer to do it. So that's how I'm going to do it. So I have 2 to the 1/2 minus 2 to the 1/3 and 2 to the 1/2 minus 2 to the 1/3. So distribute this out and you just kind of add the exponents together, right? And because we're going to be adding exponents together, what I like to do is I like to make sure that everything has the same base or as close to the same base as I can. And also like to make sure that all the denominators are the same. It just makes it a little easier when you multiply them all out. So all my denominators and my exponents have 2's or 3's. So the common denominator there is going to be 6. So 2 to the 1/2, I can rewrite as 3/6. 2 to the 1/3, I can write as 2/6. 2 to the 1/2 again is 3/6. And then 2 to the 1/3 is 2/6. Right, I'm just doing it this way, so when I distribute this stuff out, all I have to really do is just add the exponents together. Right, so if I have 2 to the 3/6 times 2 to the 3/6, that's 2 to the 6/6, or just 2. 2 to the 3/6 again, multiplied by negative 2 to the 2/6, gives me negative 2 to the 5/6. And then negative 2 to the 2/6 times 2 to the 3/6 gives me negative 2 to the 5/6 again. And then negative 2 to the 2/6 times negative 2 to the 2/6 gives me a positive 2 to the 4/6. So what I end up getting is this 2 stays the same, that's okay. And this 2 right here becomes 3. I can't do math right now. Divided by 2 becomes 2/3. So 2 to the 2/3. And then for this part right here, I have 2 to the 5/6 times 2 to the 5/6. So I have 2 of those 2 to the 5/6. So I can rewrite that as minus 2 times 2 to the 5/6 because I have 2 of them. All right, sorry about that. And then from here, we're just going to keep simplifying it down as much as we can. I guess you can just rewrite this as 2 minus 2 to the 6th root of 2 to the 5th, which is 32, plus 2 to the 2/3, which is the 3rd root of 2 squared, which is 4. You could write it this way if you want to, but I don't think this part really specifies to write it as a radical or exponent. Yeah, it doesn't really say anything like that. So you really could have left it in the top one as well. I know me personally, I would have been okay with this answer right here on the top because it is simplified. But if we do say put it in radical form, you should put it on the second box right here. So it really depends on how the question is being asked because these two are the exact same thing. They're both pretty simplified. One is just in exponential form while the other one is in radical form. Any questions about that? Are we okay? If not, we'll keep going. We have 2 problems left. All right, 1 plus root 6 all over 2 minus root 3. So the problem with this one is that you cannot have any type of root or fraction exponent in the bottom of a fraction. So I have to get rid of that negative root 3. And you can do that by multiplying the top and the bottom by the reciprocal. Oh, sorry, not the reciprocal. I forgot the term for it.
Conjugate.
Conjugate, thank you. The conjugate of the bottom. So instead of 2 minus root 3, it's 2 plus root 3. So I'll multiply top and bottom by 2 plus root 3, and I'm going to see what I get. So for the top, I can distribute the 1 in to get 2 plus root 3, then distribute the root 6 to get 2 root 6 plus root 12, because root 6 times root 18, sorry. And then on the bottom, when you have you multiply 2 conjugates together, all that is a difference of squares. So what we get is just 2 squared minus the cube root of 3 squared. So the top, we can't really do anything with that. It's just going to be 2 plus root 3 plus 2 root 6 plus root 18 all over the bottom, which is 4 minus the cube square root of 3 squared is just going to be 3. So it just becomes 2 plus root 6. So I'm going to put root 6. Sorry about that. Root 3 here. 2 plus root 3 plus 2 root 6 plus root 18. And that's going to be your final answer. Any questions about that? Does that make sense? I guess you could reduce root 18 to 3 root 2, and that probably would be better, but yeah, just go ahead and do that. Root 18, that's the same thing as 3 root 2. Any questions here? Are we okay? All right, let's keep going. One last question. Here, this is one of those weird ones where you can take the square root of like 13 plus 4 times root 3 and make it into a perfect square trinomial somehow. So for this one, I have 13. And I'm going to figure out what 2 numbers can I use where one is a perfect square and the other one has a square root of a root 3 add up to 13. So what I'll do here is I'll start looking at all the perfect squares that are less than 13, which luckily for us aren't really much. We have 1, 4, 9. It's 1, 2, 3. Yeah, and then that's all we can do. Those are all the combinations we can do. Where with 1 we add 12 to it, 4 we add 8, and 9 we add 4. So these are all my combinations I can use that add up to 13. Right? Right away I can cross out 9 plus 4 because I know that the square root of 4 equals 2. And what I want is for that second number to have a root 3 when we take the square root of it. For 8, the square root of 8, that's 2 root 2. So this isn't going to work either. Now 12, the square root of 12, that is 2 root 3. So this is
Wait, why is 13 equal 4 plus 8? And 4
because
plus 9.
I can't, it's been a long weekend and I cannot add. Plus 9, sorry. Well, either way, it's not going to work though, right? Sorry about that, but thank you. It's going to be 9. And yeah, that doesn't work either because the square root of 9 is 3, and that still doesn't end with a square root of 3. Sorry about that, but thank you for pointing that out. Either way, the one that's going to work is 1 and 12 because 12 gives you 2 root 3 and 1 is a perfect square. So I can take this and I can rewrite this as the square root of the bigger number goes first, so the 12 plus 4 root 3 plus 1, where the 12 and the 1 came from these numbers we just found. So the reason we're doing this is because I want to put this in the form a squared plus 2ab plus b squared, or I want it in a perfect square trinomial form. So before I factor this out, I'm just going to double check that this is actually a perfect square trinomial. So I'm saying that a squared is 12 and b squared is 1. So that means a is what we just saw, which is 2 root 3, and b is just 1. So 2ab should be 2 times 2 root 3 times 1, which is 4 root 3. And that's exactly what we have in the equation, and that's why this works. So I know that when I did this thing right here, I did put it as a perfect square trinomial form. So that means what's underneath the square root can factor out to a plus b all squared. So in this case, it factors to 2 root 3 plus 1 all squared. Well, the square root and the square cancel out, and I'm left with 2 root 3 plus 1. Any questions about that? Or-
Just like leave it like that for a second.
I'm sorry, Arjun, go ahead.
Oh, I was just asking if you could just like leave it like
Yeah,
that
sure, I'll leave
for-
it. Yeah, sure. All right. I mean, that's all the problems I had for you guys. That I saw, what I thought would be useful for you guys in the quiz. But we're still changing the quiz. We don't know what we're gonna do with that yet. But does anyone have any regular questions for me? Any problems you want me to do, or anything like that? Because that's all I have for you guys. Arjun, go ahead.
Could you go over I think it's in 12.2 part A.
I'm sorry, say it again.
It's in 12.2 part A. Could you go
12.2
over 50? Could you go over 53?
53. Oh, that's the one that says like solve for you.
Yeah.
Let me pull it up. Let me actually end the recording though, because that's all I had. Can't take a picture of 48. Yeah, go ahead, Art. Abraham, go to that real quick while I pull up the other problem.